Hi everyone, so I'm just going to do a quick review. I haven't looked at this exam in like over a year, but it might have like some things that we haven't covered yet or something, but we'll just it along the way. You can always pause the video and try the problems on your own, because I'm just going to kind of fly through this, alright? Because this is just all supposed to be a review for your exam. Okay, so to start, what's the relationship between A and C? Okay, well C is not an element of A. So that's not that one. Okay, so let's see. So 3 squared, that's 9. So any integer bigger than 3 is going to give us, squared is going to give us something bigger than 9. So that's just going to be all the integers bigger than or equal to 3. Well, that's what C is. A student pointed out to me that I forgot to think about the negative integers in A that are not in C. Something with Z minus C. So Z minus C is going to be all the integers less than 3. So B doesn't have all of those, but it has some of them. So it's a strict subset, which means it's a subset. So we're good there. 3 is an element of C. Cool. So A is something with B, needs to get the empty set. So they have nothing common, so it'll be the intersection. Well, A and C are equal, so if you union them, you get A back. Okay. So negate the following statements and state whether the original statement is true. Alright, negation. So we're going to switch from for all to exists in X and the integers, because we still want to talk about the same place that they're talking about. Alright, so now this is an if-then statement. So remember, the negation of the if-then statement is an and statement. Okay, so we have what are we going to have? X squared odd and X even, right? Because it's P and not Q. Okay, well, I know that that doesn't happen ever, so the original. OG true. That's what I'll say. Okay, so now for this one, negation. So we switch from exists to for all X in the rationals, square root of 2 is less or equal to X, and 5 is bigger than X. Oh wait, I forgot to negate it, sorry. So negating this, we need that, and for this one we need that. So remember, if it has the equals to, we need to flip-flop it, because that's an or statement. Alright. Okay. Ooh! Yep, and or. Whoops, daisies. Okay, so let's say that this is P, this is Q, so then it would be P and Q. So then our negation of that should be not P or not Q. Sorry, I got a little ahead of myself there. Okay, so not P or not Q. There we go. Now it looks better. So either it's bigger than square root of 2 or either it's less than square root of 2 or it's bigger than 5. Bigger than or equal to 5. Well, that's not true because 2, we can use 2 as an example. Okay, so OG true, because there exists someone who's in that realm who is bigger than square root of 2 and less than 5. Yeah, 2. We can pick 2. Negation. For all n in the integers, there exists an m in the integers such that m squared is less than or equal to n. Let's see. So, let's think about this. Okay. So, probably where things are going to get a little funky is when n is negative. Because m squared is always going to be positive. So, like, let's say n is negative 1. Is there any integer that squared is going to be less than or equal to negative 1? No. So, OG is true again. Ooh, funky. Okay. Alright. 3. In each of the following statements, x, y, and z represent sets. Note that these sets need not be distinct from each other. Right, so they could be equal. State whether or not the given statement is true or false. Okay. So when you're writing this on the exam, you should write out the whole word true or false. Because, you know, sometimes people try to be tricky with, like, that kind of stuff. That'll just get 0. Okay. So for all sets, Oh, this is a good question. This is tricky. So we know that the empty set is always a subset, but the set containing the empty set, not always true. Okay? But this is true, but this is something different, so that's false. False. Okay? So this is probably what people think of when they call it true, but so for all x, there exists a y such that x minus y equals y minus x. Yes, that's true. In fact, you could choose y to equal x. So some evil scientist hands me an x. I'm just going to hand them a y that equals x. And then that's going to be true. Alright, so if x is a subset of y and y is a subset of z, then x is a strict... strict subsets. Okay, so if x is... So let's first talk about subsets. So if x is a subset of y, y is a subset of z, then yes, x would be a subset of z. And then if there's an element in y that is not in z... Well, there's an element in x that... No, there's an element of y that's not in x. Sorry, I got that backwards. And there's an element in z that's not in y. Then there's definitely an element in z that's not in x. Yes. Okay, so this is true. Alright. For each of the following, read the directions carefully and give the appropriate answer. Let A be that, B be that. Give an example of the function that is injective, but... So we're not going to be talking about surjective. So we just want, give a function that is injective. Okay, so let's see. Well, we can literally just pick out, so f of, so f of 0 equals 2, f of 1 equals 3, f of 2 equals 4, so we could just do that. But what am I doing? I'm just saying f of x equals x plus 2. Okay? And that will always land me in B. And it is injective because no two elements over here hit the same element over here. Awesome. So that's what I'm going to say. Alright, so let h be from R to R be defined as that. Assume without proof that this is a bijective function. Okay, so bijective function, we'll ignore that for now. We're just going to say injective function. Okay? Alright, because we haven't learned about bijective yet. Next week. So h of x, oh yeah, so, oh wait, we're already assuming that that's true. Oh, we can't do this problem at all. Sorry, friends. Okay. Prove using contrapositive and contradiction that that is true. For all A and B. Cool. Indicate which proof you're using by circulate the appropriate... Oh, or. Okay, sorry, or. I could do both, I guess. That might be helpful. I'm not sure. Okay. So let's call P. P is the statement a squared b plus 3 even. And Q is the statement a even or b odd. Okay, so contrapositive would be, so this is P implies Q. Contrapositive would be Q, not Q, sorry, implies not P. Okay. So what does that look like? That would be A odd and B even implies that A squared B plus 3 odd. Okay, because contrapositive, we just flip it and negate both sides. Contradiction, though, so the negation of P implies Q is P and not Q. Okay, so that would be A squared B plus 3 even and A odd and B even. Let's see. I think contrapositive is going to be easier. Well, I think both of them actually could be kind of simple because you get to assume a lot in the beginning. I'm going to go by contrapositive. Okay. So contrapositive is going to be my choice. Proof. Assume, because remember we assume the if part, because if the if part is false, then what we're trying to prove is already true. So we assume A is odd, B is even. So now we're going to talk about the definition of that. So then there exists some K and L in the integers such that, sorry, I don't know if you could tell, but I'm sitting outside, equals 2K plus 1, and B equals 2L, let's say. Okay, so consider, because remember, you can always ask your reader to consider stuff. And then I'm going to plug all this junk in. Ooh, I could have used a tricky hack, and I could have said, since A is odd, then A squared's odd. Ooh, okay, I'm going to add that in, because I actually really like that. That's going to make this a lot slicker, and a lot less, a lot less need for proof and stuff, a lot less writing. Then A squared odd, since A odd, if and only if A squared odd. Okay, so now I'm going to rewrite this as A squared. Boom. So much easier. You could do it the other way, that's fine. Remember, there's always like a gajillion different ways you can do every single proof. Alright, so 4KL plus 6K plus 2L plus 3. Woo, okay, so what am I trying to do? I'm trying to show that this thing is odd. Okay, so I'm going to want to pull out a 1 out of here, because I want it to be 2 times some integer plus 1. Okay, sometimes I usually write what I want, and I'm sorry I didn't hear, kind of speeding through this a little bit. But you can always write what you want. Just make sure that you are clear about that it's just what you want and you're not assuming what you're trying to prove. Okay? Alright, so boom, boom, boom. Since K and L in the integers, then 2KL plus 3K plus L plus 1 is in the integers. So A squared, B plus 3, odd by definition. Therefore, and so since I wrote out what my P and my Q are, I can actually use these down here. Therefore, not Q implies not P. So, by contrapositive, it's a long word, isn't it? P implies Q is true. Boom, roasted. Woohoo! Okay. So contradiction is going to be kind of similar. What you're going to do is you're going to assume all these things, and then you're going to show that something breaks. So probably how I would do it is I would assume this. Well, I'm assuming the whole thing, right? But then I set a K and an L for just this part. And then I consider this thing, and then I show that it must be odd, okay? And then I say, wait, I assume that it was even. Contradiction. An integer can't be even and odd at the same time. Okay? All right. So, let's see. What's next? Prove that that is a strict subset. Strict. Okay, so proof. All right. So first thing I want to do is I want to show that it's even a subset at all. All right, and so here's where some people get really lost with these kinds of proofs. I just want to consider some element, let's say Y, in our set, this thing. So maybe I'm going to call it set A and set B, so I don't have to keep rewriting this thing over and over and over again. And that's totally legal for you to do. You just need to remember to actually write it at the top so that the grader knows what you're doing. Okay? So consider some element Y and A. Then there exists, let's say, a K or something in the integers such that Y equals 27 to the K. Okay? So now what do I want? I want to show that Y equals 3 to the L for some L in the integers. Well, how can I change 27 to some exponent to 3 to some exponent? Well, as you might have noticed, 27 is actually 3 cubed. Fun fact. So then that's just 3 times 3k. Oh, awesome. Since k is in the integers, 3k is in the integers. So y is an element in B. Boom, roasted. So A is a subset of B. Okay, but that's not all. I want to show that it's a strict subset now. So now I want to show that they're not equal. Consider, well, let's think about it. Who would we want to consider? Who's in B that's not in A? Well, let's see. So where things start happening maybe is like around 1, 0, and -1. So 27 to the first power is 27, 27 to the 0th power is 1, 27 to the negative first power is 1 over 27. Okay, but we have 3 to the 1 in B, and so that's 3. Okay, so 3 is in B, and it's not in A. Oops. Sorry, I just locked my thing. Okay, consider 3 in B, since 1 is an integer. Okay. How did we show it before? So maybe there exists no k in the integers, or maybe we could use a different letter, that's fine too, such that 3 to the so okay. Consider 3 to the 3k, k in the integers. Can 3 to the 3k equal 3? Alright, so you can do a lot of things with this. You can do some ln stuff. So, or you could do proof by contradiction. Actually, that's probably the best. Alright, I'm going to do that. Sorry I keep changing my mind. By way of contradiction, assume 3 is in A. Okay? Then there exists some k in the integers. Then there exists an integer k such that 27 to the k equals 3. Okay, so now what we're going to do is we're going to do some of the math that we did above. So we have like, we have 3 to the 3k equals 3. Okay, well, so something we could do is we could ln both sides, or we could just look at this and say, okay, well then that means that their exponents would have to be the same. Okay, so then we would say, then 3k equals 1. Okay, meaning, so now by definition, since k is an integer, 3 divides 1. Contradiction. That's not true. Okay? Therefore, 3 is not an A. Oh. All right, so there we go. We got it. Okay. So now let's look at what we have here. Let those be Fibonacci numbers. Ooh, oh my gosh, I love Fibonacci numbers. Okay. So this down here is the definition of Fibonacci numbers. Okay. Prove using mathematical induction that for all n in the naturals, we have that a1 plus a2 plus a is that? All right, so mathematical induction. That's just induction. So proof by induction. So first we want the base case. So who's our base case in this scenario? Well, it's going to be the lowest number that we can grab. So the lowest number we can grab is 1. So n equals 1. Okay. So n equals 1. What do we have for that? Well, actually we might want to do n equals 3 because that's the first time that like something interesting happens. All right, so n equals 1 would just be a1 equals, oh, okay, so a1 equals 1. And a3, well, what does that equal? That's going to equal a2 plus a1. Okay, so this is how we want to do it. My apologies. So we have 1 plus 1. Okay, so that's equal to 2. All right. Since 2 minus 1 equals 1, done. All right, because here we would have 2 minus 1, and on this side we just have 1. Okay. I'm not sure if you can see this like volume bar, but my headphones are broken, I think. Okay, base case. Now we want to do inductive hypothesis. Okay, assume, let's say a1 plus a2 plus plus ak equals ak plus 2 minus 1 for k in the naturals. Okay, now our inductive step. You might be able to hear the kids playing outside. All right, so inductive step. Here's where I like to talk about what I want. Okay, so I want to show that a1 plus plus ak plus 1 equals ak plus 3 minus 1. Whew. Okay, so all right, so now, so I want to show that. So let's start with the left side, probably. Yeah, let's start with the left side. You could do either way. It's not going to really make a difference. It's just whichever side's easier for you. I like long summations. I don't know. So a1 plus, so consider, sorry, we need to start with that. Consider a1 plus plus ak plus 1. So true, I could leave this in part of my but I actually am going to use that for something specific. So I know something about this, right? I can look up here and now I can switch this around. So I have ak plus 2 minus 1 plus ak plus 1. So sometimes what you can do is you could put like parentheses around it or something to like really show what you're doing. Whatever is fine, just as long as you're really describing yourself and you're not like jumping steps or anything like that. Okay, so shoot, how is this supposed to help? What do I know about ak plus 3? Well, not much, but let's look back at our definition of Fibonacci numbers. So any Fibonacci number can be written like this. So if it can be written like this, we can think of our k, so we have, we can rewrite our ak plus 3. Okay, so who would our n be here from this thing? Well, our n would be k plus 1, I guess. Right, so then we would have ak plus 2 plus ak plus 1. Okay. All right, cool. So let's write that down here. So by definition, AK plus 3 equals AK plus 2 plus AK plus 1. So remember, that's not part of our induction proof. That's not part of like what we're trying to show. This is just a Fibonacci definition here, okay? Which gives us that AK plus 2 plus AK plus 1 minus 1 equals AK plus 3 minus 1. Woohoo! Therefore, by induction, oh, do I have to write all that? Yes, I do. For all n in the naturals, a1 plus da, 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 plus an equals an plus 2 or minus 1. AI being Fibonacci numbers. Okay? There we go. Awesome. So remember, your conclusion always has to talk about induction when you do an induction proof. Let me pan out. See, we had our 3 cases. Our conclusion. Beautiful. Okay. Define the function, blah, 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 via the assignment rule. Ooh, fun. Okay. Remember that a generic polynomial can be written as that. Can be written as that. Okay. Prove that t is an injective function. So we don't know about surjectivity yet. So we won't do that right now. We'll just prove that t is an injective function. Okay. So proof. Let's see. So let's talk about what injectivity is, the statement. So for all x1, x2 in our domain, so maybe let's call them like p1, p2 or something, or f1, f2. P2 and here. If t of p1 equals t of p2, then it must be true that p1 equals p2. Okay? All right, so that's injectivity for us. So you might want to label that. All right? So let's start a proof. We're going to want to start with the if part, right? So let p1, p2 be in polynomials of degree 2 or less, including the zero polynomial, such that t of p1 equals t of p2. Okay, so you might be looking at this and thinking that this is looking kind of crazy with all that kind of stuff going on. So if you think about it, t of p1 is a polynomial because t takes polynomials to polynomials. So what this bracket is saying is this is a polynomial. We're not sure what it is. It's just it's going to be p1 wherever t assigns p1 to be, but it's a polynomial, so we can put a variable out in front. So you could kind of think of this as like q of x. Okay. So we have that these two things are equal, so that means that these two things are equal. That's tomato, tomato. I just like to leave off the variables sometimes. So what does that mean? Well, we can just write out what our definition of these things are. Okay, so integral from 0 to x of p1. And so this might look weird that now we're like talking about s's or something. That's a totally different variable. Well, that's kind of the point. So we're going to be taking some integral, and then this will be our new variable. Okay, so we can't write p1 of x dx and then 0 to x. That doesn't work out. You're never allowed to do that. Okay, and we also don't want it to be indeterminate because we don't want just like a plus c at the end. We want something specific, not something generic. Well, which is funny for me to say because when we start the proof we want something generic, but once we start with two generic elements, then we want to figure out something very specific about it later. Okay? I hope that makes some sense. So for this one, maybe, oh, that's weird looking. Maybe I should choose a different variable. I'm not sure. Let's do it. We might as well. It's been a while since I've taken calculus. many years. And it's been a while since I've taught it too. Okay. All right. So here we go. So that means that these things are true. Okay. So we're kind of stuck, right? Like, what are we even supposed to do here? So maybe let's think about what we know about P1 and P2. Oh, well, we know that they're in here. So what does that mean? Well, the hints that they were so nice to give us. So with the hint that they were so nice to give us, we know that we can rewrite P1 of x as, let's say, a2x squared plus a1x plus a0. And we could write P2 of x as b2x squared plus b1x plus b0. Okay, so now if we plug those in, this might become a lot simpler for us. So we have a2s squared plus a1s plus a0 ds equals 0 to x, b2. Oh, we're not using s's on this side. We're doing y's, I guess. 0 dy. Okay. Well, we know how to take the antiderivative of these things. Okay. So let's take the antiderivative of this. What do we get? We get a2 divided by 3s cubed plus a1 divided by 2s squared, a0 divided by 1s, 0 to x. Beautiful. So this is just going to be a2 over 3x cubed plus a1 over 2x squared plus a0x. So this one's going to be something similar. I mean, if you're doing an exam, I would actually write it out, but I'm going to use the advantage that I'm not actually taking a test to not have to write that again, because it's just going to be the same thing as over here, just with b's and y's. Okay, so we end up getting this. So I've explained this in previous videos, but kind of what you want to think about is these constants are not going to like somehow produce or get rid of one of these variables. Okay, so if this piece here, so if this whole thing equals this whole thing, right, then this piece must equal this piece, this one with this one, and this one with this one. Okay, because that's the only way you're going to get those variables. So sure, maybe one of these a's or one of these b's could be 0 or something, and then that would just eliminate the whole thing. But then that means that, so like if a2 is 0, that means that b2 would also have to be 0, right? So we kind of get stuff like that. So now what do we get? We end up getting that a2 over 3 equals b2 over 3. A1 over 2 equals b1 over 2. And a0 equals b0. So what does that mean? That means that ai equals bi. I equals 0, 1, 2. So P1 equals P2. Yay! Therefore, T injective. And we already wrote the definition of injective above, so we're all good. Because remember, if you're going to have two polynomials that are equal, that means that their constants need to be equal. Or their coefficients, sorry, their coefficients need to be equal. Including their constants, but... yeah. Okay. So basically what I'm doing is I'm plugging these back up into here, and basically what I'm saying is you could replace each of these b's with the a, so then that means that they have to be equal. This page isn't definitely on the great. That's very nice of them. Oh, okay, so that's it. So that's congratulations. Woohoo. All right, congrats. Talk to you later. Bye.